So, one of the major benefits of using Cortex, ARM Cortex processors, okay, you are looking at ARM Cortex processors or ARM Cortex processors, in fact Cortex M series processors, is the fact that they are highly energy efficient. They are indeed highly energy efficient, okay. And just talking about the energy efficiency, we even express them in terms of DMIPS, MIPS per microwatt, or sometimes you express it in terms of core mark per microwatt. These are important, okay. See, these two things clearly deviate from, what does it mean? Deviates from, it deviates from the fact that you are focusing only on active current, sleep current. You are not saying any more about just that, okay, which was the microamps per megahertz that we knew, right. That is all gone now. You should consider the DMIPS per microwatt or the core mark per microwatt, which is much more important as a metric. So, point is just this. For example, if you have many microcontrollers, they might need long execution times to complete a process. So, let us look at it. Long execution time, long execution time to complete a processing task. That means it is taking too long. So, what will happen? This will increase the overall power consumption. Surely it will, right, okay. So, you must look at energy efficiency, which is a very important aspect also, okay. Now, controllers will have to, rather newer controllers are actually trying to make, they are trying to bring the gap between, let us say, the active current and the sleep current values were far apart, okay. Sleep current, I will write it far apart. This distance, this may be in milliampere, this may be in microamps, and sometimes even in, usually it is in microamps. Now, that is coming down because this guy is going closer. You see now, this is active current. So, that is fantastic. Newer controllers, they are pushing it to the right, so that you are going closer, you are reducing the gap between the active current and the sleep current, okay. So, that is a very important change that is happening in the choice of controllers, okay. This is one part of the story, folks. We will have to look at this discussion even more in broader detail, but before that we must complete the story of where we started. If you look at this picture, we started here of choice of controller. We went and did quite a few things and then came back. I want to summarize with this table that we see here. Look at Cortex M3, it is 1.25 DMIPS per megahertz, core mark is 3.32 megahertz. M4 is the same as the Drystone is the same benchmark, but its core mark per megahertz is 3.38. This is what people report, but do not forget what I mentioned to you on how the newer core mark is to be mentioned, not just in terms of megahertz but also in terms of power consumption, which is the microwatts. Okay. This is the most important aspect of what I wanted to drive home to you. Now the discussion continues to be incomplete because we have not touched upon this multiprocessor in detail. Okay. I will touch upon this multiprocessor and then I will close this discussion. Then later we will take up the question of implication in battery life, implication of all what we are saying in terms of battery life. So let us move on to understand multiprocessors. Okay. So folks, if you are tired of listening to me, let me show you a demonstration. In fact, I will not demonstrate, I will show you a picture of what we have in the labs and maybe that will help you to connect. Look at this picture here, look at what I have in my hand folks. I have this single Cortex M3 controller, single controller, small little one, has some ports here, through some flexible cable I can connect a few sensors and so on, and I can do some sense and send, and I can run it and ensure that lifetimes of these systems are quite close to the 10-year kind of lifetimes that we are talking of. But then I also have this. I am not sold to Nordic, but we have been buying Nordic processors in the lab. So because of our comfort of using Nordic processors, NRF 5340. Folks, if you go and Google this for that is this board. Okay. If you go and look up this board, you will realize it has 2 processors inside. Okay. You may now ask, oh, is this meant for beyond the sense and send applications? Yes, indeed. It gives you good performance. Okay. All the conflicting resource requirements I was talking to you about, particularly the CPU resource, is out because you have one CPU doing one part, which is perhaps high frequency sampling, and there is other CPU which is just looking at the communication interface. Now the question is, how do you make the 2 processors work together? Okay. And that is an IP which nobody is going to tell you how they end up making these things work. Also has moved, the world has moved on to have on these kind of development boards. This is a development board. Okay. These are development boards. This is based on Nordic 9160. This is a Nordic 9160 kit. Okay. And this board is quite advanced because it can essentially connect to the internet over a narrowband IoT connection, NB IoT connection. So we got this, you can put a SIM card and you can take the service of an operator and you can connect sensors to it directly over a cellular infrastructure, terrestrial infrastructure. You can start uploading data, or you can have a cluster of sensor nodes which communicate to this central system. This is like a gateway. This in turn communicates to the outside world using the SIM connection that we have. So things are moving forward folks, and I am sure you appreciate that these are important developments happening, going away from the Telos B and the Iris and the Mica and the Mica Z modes to something which is a lot more advanced, where you have multiprocessors. So let us discuss a little bit about multiprocessors and also the hard problems that are there in using a multiprocessor yet maintaining ultra low power. That brings us to this, what I wrote on the screen here. Is low power possible at all is the question. Okay. The answer is a big yes, provided you remove the interference in time, power and clock domains. This is very important, that is you are talking of separating the two processors in terms of time, in terms of power and also in terms of clock domains. Okay. That is where the whole issue of sense and send applications are very simple, but the same kind of controller which is used in sense and send, if it is now used for let us say surveillance or even tracking, okay, these systems cannot respond to unpredictable events. That is the problem. Okay. That is why you must motivate yourself to move towards the multiprocessor environment. Okay. If that is indeed the case, how do multiprocessors communicate among themselves? Well, very well known is the shared memory architecture. Okay. The shared memory architecture is something that has been used for several decades now, and the energy consumed grows by the amount of useful task execution that is performed. Systems use different power and clock domains, right. So, from an energy perspective, coupling of power and clock domains is important, that is okay, but then shared bus couples these domains, right, the power and the clock domains. There is a shared bus, and this shared bus coupling these two, power and clock, is not at all good for safety critical automotive applications, automotive or even aerospace applications. Okay. So, that is a big problem. Okay, that is one thing. So, which essentially means the principles of separation of concerns and isolation of independent functionalities are actually violated, and power management requires interaction with many hardware and software layers here, that is the problem. Now, as a rule, unnecessary interference and dependencies introduced on the hardware layer can rarely be decoupled by means of any other layer, software layer that comes into picture. So, in a way the existing mechanisms of shared memory are not good in terms of separating the clock and power. What about interference in time domain? Well, that is true, you can use semaphores and locks, right, for mutually exclusive access to resources, but the problem with that is you lose your independence in design. Independent design is a goal, right. So, the issue of addressing multiprocessors in the market even for manufacturers is not a straightforward thing. They how much can they bring in the separation between time, power and clock domains is indeed the real crux of the problem, and you have to study the data sheet of any multiprocessor systems in careful and in great detail from this perspective. Okay, this is important. Now, is there a solution at all is the question. The answer is yes, why not. There are new things that have come up, not in the embedded domain but well known in the distributed computing world, where people talk about distributed memory, synchronized message passing, queue based communication and so on. All these are not really attempted in the embedded world. So, now you see you can open up a new area of looking at, can I take two commercially available processors which are heterogeneous by nature. Think about something like a Atmel processor and a Nordic processor, and you are putting them together. You have to manage to somehow connect them together. That means you have to build in that intelligent layer which does synchronized message passing, for instance, queue based communication or any one of the things. You have to read them in detail, understand what kind of construct you would like to do between the two to sort of connect them together, and that becomes a very interesting piece of hardware which could be used in industrial applications. And we listed the several industrial applications in the past, and I will connect you back. What were the multiprocessor applications? Let me read out: industrial IoT applications, control and supervision, process control and supervision. P is gone for some reason, I will put it back. Structural monitoring, personalized medicine, all these systems can use potentially multiprocessor environments. Understanding the benchmarking part, we said there are two, right. We said about dry stones and also we mentioned about the core mark. We must go and have a look at the core mark website because there is wealth of information and that will help you to understand even further on performance of a controller or an SOC. What did we say about an SOC? SOC has peripherals, has the core CPU, right, and the CPU has sleep modes and active modes, all are there. Now you should be able to pull out these components and say all the peripherals, how do those perform, how does the CPU perform, how does the CPU, what is the kind of power consumption that the CPU utilizes when it is in deep sleep. All these performance related issues are there in the website. So let us go to this website and have a look. I will just give you an overview. This EMBC actually stands for Embedded Microprocessor Benchmark Consortium, okay, and spend enough time understanding this in great detail because all about core mark is out there, okay. And what actually the as far as power consumption is concerned, if you are interested there, which is of interest in this course, is our ULP mark suite offers a core mark variant that clearly defines how to measure and record core mark power in a uniform way, making comparisons a snap. So let us look at this ULP mark, okay. So if I go here to this website, it simply connects to ULP mark, okay. Again you read these things, it will tell you about the benchmark quantifies the many aspects of ultra low power MCUs and so on. If you read it carefully, you will find these three are very interesting, okay. This is the ULP mark family of benchmarks. ULP mark core profile, true energy cost and of deep sleep, okay, true energy cost of deep sleep. Now ULP mark peripheral profile, common peripherals energy impact on deep sleep. The third one is ULP mark core mark, active power using core mark as the workload, okay. So he has defined in this here itself they define what is known as a workload, okay. So now let us see as I mentioned, core mark is very specific to CPU, this is the key takeaway, unlike dry stones which was heavily dependent on the you could tweak the compiler related, right. So that is not the case here, it is completely CPU related. So let us look at this ULP core profile. What does this core profile tell you? It tells you some interesting things. This is an interesting site, okay. So you must read this very carefully because this picture that you see is what we are going to use heavily in our battery life calculations. What do you have on the x axis? Time. What do you have on the y axis? Energy. Often we plot not energy but current, we plot the current versus time. So when you get current versus time and you know the operating voltage, you can easily calculate the energy, okay. He has abstracted that. So he has given you one number and he is plotting energy consumption over time, he has given you this. But whenever we do a measurement in the lab, it is usually I along the y axis, time along the x axis, then you calculate each of these peaks nicely and find out what is the area under this peak, then you calculate the area under this section, add that. So take this, calculate the area of this plus area of this plus area of this plus area, you will get one number. That number you will take and use it for your further operations, okay. That is the core idea behind this picture, and that is also the reason why you must visit this website to get a very clear view. Let us read it. It says ULP core mark profile focuses on MCU's core, specifically energy cost in sleep and the transition to and from active mode. Folks, do not forget this. I mentioned several times in this course that if the controller is sleeping and you give it a timer interrupt so that it wakes up, it is going to take a huge spike of current, we mentioned that spiky nature of current depends on the type of oscillator that you use. If it is a crystal oscillator, remember the oscillator takes a long time to settle down and current consumption is quite high, however the clock is stable. Whereas if you use internal RC oscillator, it might be fast, it can't support very high frequencies, maybe the power consumption is also low. So now design means you will have to think again where you want to apply internal oscillator or where you want to apply the external oscillator. So anyway, coming back to the focus here, this typically could be because of that energy consumed here, could be because it has woken up, alright, it has woken up, done some activity and gone back to sleep, and then again it has come back to wake up state, it is active now, it has consumed some activity and gone back to sleep. Now what all are possible in this active state is the question. You wake up the crystal oscillator, you apply a timer, you wake up the controller, it comes back to full frequency of operation, clock is fed to several of the peripherals, clock is ready now, clock is available, you may do sense, little process and send, sense, process, send, sense, process, send. That means send means what? Radio. Radio is also shown here, it will also be shown here in this active. So wake up, compute, sending, all that will do, then it will go back to sleep, again the same thing will happen. This can be equated to something like a periodic sensing of the environment. It could be like temperature, it could be like humidity and so on, okay. Something which does not change drastically, but something that you need periodically, some one data point you need periodically, okay. Now this website is so critical, it tells you so many things. If you look at the down sentence here, he writes, while the active portion of the benchmark is only running roughly 3% of the total runtime, it requires data to be saved during deep sleep through the use of retention RAM. Since it is rare that the sleepy edge node would clear its RAM after every sleep cycle, the exit and enter costs of retention RAM illustrate true energy costs of sleep modes. There is more of it than just a data sheet number. Amazing sentence, I will tell you why. Go back to your Nordic processor, there are several modes which you can put the Nordic processor to, low power modes of the Nordic processor. One of the Nordic processors mode you might have observed is with RAM retention, it is there, please read the data sheet, it is out there, and it is important you do that homework, and he is actually referring to that here, he is actually referring to that with RAM retention. So that is out there. So this RAM retention is also and he tells you that it is not that, so that means there is the RAM which is kept alive. You can't say I am going to switch off the RAM because it has sensed, put that stuff in whatever sensed value is sitting on the in the RAM. So he says it's since it is rare that the sleepy edge would clear its RAM after every sleep cycle, the exit and enter costs of retention RAM illustrate the true energy cost of sleep modes. You cannot afford to clear the RAM, so it is out there, okay. Now during the active portion of the test, what all he has done to benchmark is the question. I gave you an idea of crystal on, then sense, then transmit, sense and send, right. I have given you that idea, but when you are benchmarking, that is not what you should be doing. What you should do is these things are what you should do. This is the key difference between benchmarking and thinking that you want to use it for some application. Your application could be one thing, your benchmarking is important. So what should you do? Generate 20 GPIO pulses, perform an 8-bit linear interpolation, perform 16-bit integration, compute a 7-segment LCD binary conversion, search for a substring in a string, perform a small bubble sort, permute the bits of a string based on input and previous state. Do all these are the tests that you have to put. Take your multiple processors that are in front of you, use those multiple processors, run these tests. If these tests are done, you can generate a number which you can corroborate on this website and use those numbers rather than worrying about your application. Okay. If you do this, your application will automatically be energy efficient. You do not have to do crystal oscillator start, and you do not have to do all of that. That is all, it all be amortized into these tests. Moreover, you are more interested in the proper comparison between different, because our whole exercise was how do I choose a controller from a low power perspective, from a performance perspective. So you have to do these things much more importantly. Great. Then so I hope that part is clear. So I will now show you that there are other possibilities of peripheral profile. That means it takes into account several other peripherals of an SOC, and it gives you the slot here. For example, ADC is important, right. So conversion rate is 1 kilohertz, then you have the frequency which is 32768 hertz, that is 32.768, the low frequency crystal oscillator which is out there, and so on. So all the other related oscillators and frequency of operation is also mentioned here. For example, if you look at 9, they use the 1 megahertz frequency. Here it is all 32768 kilohertz hertz, and here it is the 1 megahertz frequency. So all the active parts are also mentioned here, and so are the parts related to the core controller also. So let me go back and show you. The third one is here. Yeah, I must go back here. Right. You see the ULP core ULP mark core mark. Here you can obtain the benchmark of several controllers which are out there already. Yeah, so if you look at this core profile, there is something even a little more interesting that you can look up. So let us see what that core profile is. Core profile is coming from here. Yeah, core profile, this is the core profile. So true energy cost of deep sleep, some standard controllers have been characterized and those will come here. Okay. You can choose the controllers of interest whichever you wish, and then basically you can say compare scores, and then you can say I want to do that. I also want to do RAM retention, right, and choose your RAM retention parts. If you remove, you can see things change automatically. So I would want you to do this. You can play around with this. You can tick on core. You can see ST Micro, Cortex M4, Cortex M33, so on are all mentioned here. Okay. RAM retention, there you are. I will choose this, and then once you are done, or you want to choose any controller of interest, you just say compare scores. Okay. There you are, you get this scores, and you can start examining these scores in great detail. So I would like you to explore whatever we discussed in the class with respect to what is shown here. Okay. And we will see if we can look up some exercises as well based on what you read in this data sheet. Okay. That is about what I wanted to say about benchmarking controllers for your application. So please do spend time understanding core mark. Thank you very much.